Everyone, welcome to the IS Friday seminar. Today we are very happy to have Yichul telling us about non-invertible symmetries, boundaries, and TQF.
Thank you, San, and thanks everyone for coming. So the talk will be about non-invertible symmetries generated by topological line defects and boundaries, some interplay between them, and some recent developments. So the plan of the talk. So I want to start slowly and then at the beginning review some basic known facts about topological lines and how they interact with boundary conditions in 1+1D conformal field series. And then the second part of the talk will be about more recent developments. This will be based on two papers that we wrote in collaboration with Brandon Rayan and Yunxin Zheng. Both of them are at Stony Brook. They are mention some relation to 2+1 dimensional topological quantum field series, and some towards the end of the talk, I mention some application to entanglement entropies. Okay, so let me start by reviewing some basic things. So the setup is that we'll be focusing on 1+1D conformal field series. And my conformal field series is defined by abstractly defined by a collection of primary operators. They have some conformal weights. The coefficients. And if you want to think about topological line operators in this setup, so in general, the easiest example of a topological line would be that if your theory has a continuous global symmetry, and you can take the conserved nodal current and then integrate the nodal current along a one-dimensional locus. That's going to define a line operator, and then you can show that it is topological. But there are many other examples of topological line operators which do not admit this expression in terms of integral of some local operator across one-dimensional locus. So I'll tell you how to think about these topological lines in a more abstract setting. So in other words, when I given this abstract CFT data, how do you know there are topological line operators in this direction? So if you like, I want to give you, say bootstrap axioms. Or topological lines. And the series of topological lines, what are the minimal requirements that you want to impose on these topological lines? First, I'm going to quantize my theory on a circle. So this is a spatial slice. And Euclidean time direction. And just to remind everyone, so the space inside this circle Hilbert space being one-to-one correspondence with local operators upon conformal transformation. And now, if you have a topological line operator, one thing you should be able to do is to wrap the line operator, say X, across a time slice, and you can push this topological line downwards and then act on the state. So that's going to define an operator acting on this Hilbert space. So X can act on space on the circuit Hilbert space. Just to emphasize that this is an operator, I'm going to put a head here. And you map this picture to a plane. This corresponds to encircling your local operator, the topological line. then this action corresponds to shrinking this topological line, and then we define a new local operator which is this. And you want to require that this operator comes from a topological line operator, meaning that inside Euclidean correlation functions, you should be able to deform the shape of the topological line in an arbitrary way. Meaning that I want X operator to commute with the stress energy tensor T mu nu. Another one, you require operator to commute with every gross origin operator. Okay, so this is the first section. Yeah, by the way, please feel free to interrupt me with any questions, and then also let me know if I'm going too slowly or too fast. Okay, so second. So now again my theory compiles on a circle. And instead of wrapping the topological line across the time slice, you can let it extend along the Euclidean time direction. At each time slice, I have my spatial circle. But at one point at a spatial circle, I have an insertion of defect in this case. So what it means abstractly is that to each topological line, X, I associate a defect Hilbert space. H sub X.
What in the world would that assumption mean for a line that does come from a conserved current?
Oh, yeah. If the line comes from a conserved current, then this means that when you go around the spatial circle, your operators will be there's some holonomic group action. This will be a twisted boundary condition.
If you do have a conserved current, you can make a twisted boundary condition.
Exactly.
But I don't think naturally the definition, with X being the line integral of a current, is going to do that. What do you think the twist would be by? The data doesn't even define a group bond.
Oh. We need to exponentiate it.
You could exponentiate, but the question didn't involve exponentiation. You told us that you consider the integral of a conserved current on a line.
Let's say we have
I'm taking literally what you said at the beginning. You said that you consider the integral over X of a current to be an example of a line operator.
Yes.
I suspect maybe you want to withdraw that and not regard it as an example. But if you do regard it as an example, you should be able to say what the Hilbert space is in that case.
Yeah, so yeah, I'd like to give an explicit example, but roughly speaking, let's say we have some conserved U1 power segment.
Yes. I know that if you have a J mu, you can construct a twisted Hilbert space,
Yeah, exactly.
but your construction will not lead to it. You probably do not want to regard the integral of the current over X as an example of a line operator. You probably need a definition of line operator that works so that
Yeah. I mean, the thing is that if the theory has a Lagrangian description, say like in compact position, let's say we consider the U1 momentum symmetry, the integral of the current density, when I insert that into Lagrangian, I can remove that by field redefinition where the compact position shifts by a constant amount across the line, so that it's going to be equivalent to a twisted boundary condition.
you're correctly describing what would happen if you took over X, the exponential of the integral over X of your line operator. But what you told us at the beginning, perhaps it was a misstatement, or perhaps you want to withdraw it on further thought. But what you said at the beginning was that you regarded the integral of the current over X as an example of line operator.
Exponential.
Fine.
Okay, yeah.
That was crucial, as you.
Yeah, sorry. I was being sloppy, but I think this shit. Okay. Well, if you map this to a plane.
Let me ask a related question. So, why should the insertion of that operator lead to a unitary boundary condition?
why does this?
It's an axiom, but.
Yeah, why does the Hilbert space?
Yes.
Yeah, it's part of fiction. So yeah, it's not always the case. Even in a unitary theory, you can find topological lines where the twisted Hilbert space actually doesn't respect unitarity. But
And I'm asking because when you have, I guess you're allowing non-invertible symmetries.
that's right. That's right.
So, well, remind me what happens if you have a non-invertible symmetry along that direction? Do you have a well-defined defect Hilbert space?
Yeah. So yeah, there are examples of non-invertible topological lines X where the Hilbert space is still unitary. So yeah, non-invertibility. Yeah, and there can also be, even for invertible symmetries, there can be examples where the Hilbert space doesn't have a unitarity. For instance, just the U1 symmetry. Logically, we have this kind of line. You can take imaginary alpha that will have a spectrum in the twisted Hilbert space which doesn't satisfy a unitarity bound. Yeah, so yeah, these two are unrelated. Invertibility and unitary. But
Sorry, Edward's question actually confused me. So, what is the actual definition of the topological operator? Why is the integral of the current not that?
yeah, sorry. If this is confusing, then let's forget about it. I'm just giving you X set of axioms, right? So you can just take this as the definition. And for throughout the talk, yeah, maybe this made more confusion. But I mentioned continuous symmetries at the beginning, but for throughout the talk, I'm gonna only focus on finite symmetries.
So let me ask about first point, first assumption. So that excludes high spin symmetries, right? So you're not considering
Yes.
logical.
Yeah. Okay. For some more, related to the, I'm focusing only on internal symmetries. So I'm gonna explore the space-time symmetries. So for instance, conformal symmetry is not gonna satisfy this assumption. I'm putting a restriction. So, okay, if you do a state operator correspondence, then states inside the defect Hilbert space will map to operators that are attached to at the end of the topological line X on a plane. Before moving on, one important thing is that because the line is topological, the presence of this topological line does not really ruin the conformal invariance, meaning that this defect Hilbert space is sub X is in a representation of the Virasoro algebra. So this Hilbert space still decomposes into a Virasoro multiplets.
Sorry, could you please write explicitly what do you mean by a timeline defects with the local operator attached to the endpoints? Just confused with this.
What do you mean?
Yeah, so here you have a defect X and you attach a local operator at the endpoint, right? What does this mean? It gives a new operator or?
Let me just give an example maybe. So let's say you had the G2 symmetry in your theory. Then you can take X to be the G2 symmetry generating topological line. And operators, this picture means that this operator OX is attached to a G2 principal. If you have a G2 charged local operator, say O prime, try to compute the correlation function between these two. And there, in the correlation function, there will be a principal. When this O prime, say, goes around this operator, you pick up a minus sign. That's what this means.
priori it can be empty, the Hilbert space at this stage, right?
This Hilbert space, yeah, in principle, this can be empty, yes.
An example is the fermion Ising model, for example, 1 + 1 to Ising.
Yes, yes, exactly. Okay. So the final axiom that I'm gonna present is that 1 and 2 must be comparable with each other under a modularized transformation, meaning that let's consider the theory defined on a torus. I'm going to draw a scale to represent the torus. So these two sides are identified, and these two are identified. I'm drawing a scale torus, but in this picture, I keep the complex modulus to be arbitrary. And consider wrapping your topological line along this spatial direction. So this is what I'm taking this to be the time direction. And this picture meant to present the following quantity. If you do this past integral, what you get is the trace over the circle Hilbert space, where the operator x acts on this Hilbert space, and then you have the Hamilton. Now, you want to be able to interpret this direction as a Euclidean time direction as you can rotate the picture by 90 degrees. It means you are doing a modularized transformation. So now you are at -1/tau complex modulus. The sides are identified. When you do this S transformation, now the topological line will be running vertically. This picture, this past integral computes a trace over trace to the Hilbert space of x, and you just time it. So the third axiom is that this equality must Q. Oh, sorry, Q tilde. Q yeah, so this puts some constraint on these. It says that 1 and 2 must be consistent with each other. So this is an abstract way to think about topological line operators. So originally I was planning to give some examples, but if I do, then I think I will not have enough time to get to the punchline of top. So let me just leave it there. I hope that the abstract idea is clear. So this is how you go about to find topological lines in a CFT defined by this abstract CFT data, basically, in practice. I'll give just to remind everyone some writing review of conformal boundary conditions in 1+1 DCFTs. Let's say is a conformal boundary condition. And what they do is to every conformal boundary condition, they associate a so-called Hardy boundary state. Satisfying condition, meaning that there is no momentum flow out of the boundary. And then when you have a pair of boundary conditions, then B prime, you can associate a Hilbert space This is the interval space. With your theory, where at two ends of the interval you impose conformal boundary conditions B and B prime. I'm gonna write it as space BB prime. And states inside this interval space, they map to boundary condition changing local operators near the state operator correspondence. And finally, there is a famous starting condition. It says that 1 and 2 must be compatible with each other, which I'm not gonna write down. Just to remind everyone, just means that when you compute the cylinder amplitude, you should be able to do it both in the closed string channel and open string channel, and then results must agree. And let me just introduce one technical terminology. A boundary condition, a conformal boundary condition B is called, this is the definition. It's called simple, or sometimes also elementary. If the interval space H sub BB has a unique ground space, that's the definition. I'm not gonna prove it, but a generic conformal boundary state is a superposition of simple boundary conditions. Okay. And I want to say a little bit about how these topological lines and conformal boundary conditions interact with each other. Sorry, before that, I forgot to mention something important. So when you have throughout the talk, I'm gonna focus on the following situation where I have a finite collection of topological line operators, and such that when I multiply them, the multiplication is closed among themselves, meaning that when I multiply xi and xj, I get a finite sum over these topological line operators. So I'm gonna focus on these particular cases. And with some more data that I'm not gonna explain, there are more refinement to this data, which are called 6J simples. This combined data defines something called fusion category in the mathematics literature. So the precise definition yes.
The product using the text is
No, so here they have this, they are acting on the circle hyperspace.
Is this like a OPE?
You can think of it as OP of topological lines. But since the lines are topological, you don't really have a short distance singularity.
I see.
Okay. Yeah. So the good thing about this fusion category is that you can show that these topological lines generating fusion categories, they share many properties that you expect from ordinary global symmetries. I will not give much details, but for instance, when you have topological lines, you can derive selection rules on correlation functions in your theory. Sometimes you can gauge these general topological lines in a certain generalized sense. Sometimes there might be an obstruction to perform this gauging. It signals the existence of some generalized version of toothed anomaly, which you can also use to perform anomaly matching under RG flows, etc. But the most basic thing one could say is that these operators, because of the first axiom, they come in with Hamiltonian. It's like there's a zeroth order thing to say. So in the literature, sometimes these more general topological line operators are called the generalized symmetry operators or non-invertible symmetry operators. And this multiplication rule, this is called fusion algebra of topological lines.
Is it for any CFT or for rational CFT?
Oh yeah, for any CFTs, the theory may admit certain set of topological lines.
But can it be infinite so that it's not?
Oh yeah. So that was part of the assumption. So I assume that I somehow found a finite collection of xi's in my given theory, which might not be rational, such that the multiplication is closed. So this is part of the assumption. Yeah, in rational theories, theoretically you can always find such finite collection. Okay, going back to the boundary conditions. So maybe let me write this way. So let's say you have some conformal boundary state, Cardi state, B. One thing you can do is that to act with topological line operator on this Cardi state. So in general ground, because we are fusing a topological line operator to a conformal boundary condition, we expect the result to be also to define a conformal boundary condition. And in fact, if you look at, for instance, the first condition for the conformal boundary condition, that's satisfied by this new guy, because this X hat comes with all the Virasoro generators. The claim is that this is also a Cardi state. And since it's a Cardi state, generically, this decomposes into a linear superposition of simple Cardi states. These are simple Cardi states with some coefficient. And then the axioms of conformal boundary conditions requires that these coefficients are non-negative integers. So what we have here is that to each topological line X, we are assigning a matrix with indices running over simple boundary conditions, where each matrix element is a non-negative integer. And this is known as non-negative integer matrix representation. In short, this is usually called NIMREPs. The point is that, let's say I had a theory with this finite collection of topological lines forming this fusion algebra, then when you have a multiplet of boundary conditions which transform into each other under the action of topological lines, they form a NIMREP under the fusion algebra. And there is a more refined data that you can again associate to these NIMREPs, which are called boundary boundary situation works. When you combine the data on NIMREP with boundary situation works, they form something known as a modular category. And there's this fusion category of topological lines, which are denoted as C. The precise definition is not going to be important. So throughout the talk, whenever I say a modular category, you can just think of that as a multiplet of boundary conditions. That's what I mean. Okay, so far this was a review. And the rest of the talk, the central object that I want to consider is that I want to define my theory on a finite interval, this interval Hilbert space, say B1, B2, to conform boundary conditions. I want to find a set of symmetry operators generated by topological lines that are stretched between the two conformal boundary conditions, which commute the Hamiltonian open string channel Hamiltonian. This means that I want to be able to move this topological line up and down. So like it must commute to time evolution. And inside the bulk of the interval, this line is topological, so there is no problem moving it up and down. But since now the line forms a junction with these conformal boundary conditions, you need to also make sure that you can also move the junctions up and down. Let's try to understand a little better what this junction correspond to. So generally you have some choice of junction operators. Say O here. And let's forget about this side for a second and focus on this configuration loop. If you do so I'm considering, I'm asking what kind of operators can sit here. If you perform a state operator correspondence, then this operator O adds to a state inside the Hilbert space, where you have an interval with conformal boundary conditions B2 and B2, but at the middle of the interval, you have this topological defect sitting there.
Is it not just that you have B2 on both sides of the operator, and you have B2 and B primes and scholars?
That's a great question. So in general, if I enforce this to B2 to be the same, then this Hilbert space could be empty. So a more general case is that you have a B2 prime. I'm gonna generalize to that case in a bit. Okay, so to say that this we want this junction operator to be topological means that we want this state to have a zero conformal weight. And let me state this without a proof, but you can prove this. This is that the number of linearly independent states that have conformal weight 0 is actually determined by this non-negative integer metric representation NIMREP. So number of these states with zero conformal weight. We can show that this is equal to this NIMRET coefficient. And then as Juan pointed out before, this number could be zero. In this case, you just don't have such a choice. And even more generally, I can consider a configuration for IP1 here, P2 here, and say different boundary conditions P3, P4. Then the number of linearly independent choices for topological junctions here and there are determined by the NIMRET coefficients. So for each choice of the topological line X and each choice of junctions G and W, you can define an operator X set of GW, which maps your state in the HB1, B2 Hilbert space to a state in the B3, B4 Hilbert space.
Do you want to put the transpose or X bar in one of the two? Because the direction.
Yeah, I'm being a little bit sloppy here, so it's yeah, maybe let's put a bar here. Okay, so now this operator by construction, so this will commute with the Hamiltonian. Maybe this map, but it commutes with the this open string Hamiltonian.
What you really mean is that the Hamiltonians are different for the
Exactly.
sides.
Yeah, so maybe let me write it correctly. So what I mean is that this for the B1, B2 will be the same as this. And then if you have two such operators, X prime and Z prime, W prime, and say these three prime, B4 prime, you can also multiply two such operators. So what I'm gonna do is to consider a collection of both such operators. In this set, you have a notion of multiplication. You have a lot more structure, but I'm gonna explain. So this forms an algebra. And it acts on this interval Hilbert space called the acts on this expanded Hilbert space, H tilde. Where I take the direct sum of all the interval Hilbert spaces. This direct sum runs over B1, B2 that are in this in a given NIMRET. And we're gonna discuss some applications later on, but the main question we want to ask is that so this algebra acts on this Hilbert space, and then you expect your Hilbert space to sort of decompose into say irreducible representations of this algebra. So this alpha labels errats of this algebra. By the way, this algebra has several names in the literature, so let me just tell you about them. So sometimes we call this algebra a name. It's sometimes called boundary group algebra. Sometimes also called the strip algebra. This because it's like the picture looks like a strip. Sometimes it's also called the annulus algebra. And I'm gonna call it a boundary tube algebra for this though. So the question we want to ask is that this is like an academic question at this point, but there will be some applications. So we want to understand what are these errats of this boundary tube algebra. So we want to have some physical understanding of what are these representations.
It's a question, in this algebra, not every two elements.
It's a great question. So the let's say you had like so this must like to multiply them into like match the like incoming and outgoing values. If you cannot do that, then you just define the multiplication to be 0.
It's not the same as the diffusion algebra. I mean, I guess you can multiply them in the back and get diffusion.
Exactly, yeah. Because of this choice of topological junctions, generally this algebra differs from the bulk diffusion. To understand these representations, the very useful tool is to utilize this relation between lower symmetries. There is an intimate relation between symmetries in 1 plus 1D and topological field theories in 2 plus 1D. I'm going to explain briefly in a bit. But this was, I guess it has a long history, but in modern, in recent years, it was explained, for instance, in the paper by the Pope. And there is also even more recent paper by more Telemann. And there is also a series of papers in the condensed mirror literature by Benz J and Shaman. The main idea is the following. So let me focus on ordinary symmetries first, because this is intuitively easier to understand. Let's say you have some ordinary symmetry described by a finite group G. This is a finite group. The claim, this relation, is that whenever you have a 1 plus 1 this theory with a finite group symmetry G, you can think of it as a dimensional reduction of a 2 plus 1 TP of T on an interval. Let's say you have a theory Q. This is a 1 plus 1 this theory. Let's say the G symmetry. Now you can realize this theory by considering following 2 plus 1 configuration. So I have a 2 plus 1 this theory on an interval, so this is the interval direction. And inside the bulk, I have a TPFT. This is just the G gauge theory. This is a pure gauge theory where the gauge group is G. In other words, I have the diagonal frequency theory here. And so this theory is put on an interval, so it has two boundaries. On one side of the boundary, the G gauge fields are freely fluctuating, and it's coupled to the your original theory of Q. So the G global symmetry of Q in 1 plus 1D is gauged in this side, where the gauge field lives in the bottom. And on the other side, you impose a Dirichlet boundary condition, where you require that your gauge field restrict to the boundary dimensions. The relation is that if you start from this side and you make the interval very small, so you do a dimensional reduction, then you recover the left-hand side, because the on this side of boundary, you set the gauge field to be 0. And also you can go the other way. Every such field clearly will define a such boundary condition by just coupling to both gauge field. And you can now generalize this picture. There is a generalized version of this picture where instead of a finite group G, you start from an arbitrary fusion category C. Now let's say you have a fusion category symmetry C acting on this theory Q. And this part TPFT is replaced by something known as tri-zero TPFT based on this fusion category C. So the details are not important, but the tri-zero construction is that you take as an input a fusion category and it outputs a topological field theory into plus 1D. And you can regard this as a generalization of the Dirac-Witten theory.
Say again what Q tilde was?
Oh, so Q tilde is just the boundary condition defined by the original theory Q. But the Q is coupled to the G gauge field.
Okay, thank you. You gauge in the symmetry.
Yes, yes. So you may wonder, what if the theory was, the symmetry was anomalous, then is it an obstruction to gauging? You may wonder that, but I'm canceling the anomaly by putting on appropriate Dirac-Witten twist in the bulk to cancel this anomaly.
Why is it useful to do this? I mean,
Yeah, I was about to say this. It is almost like a tautological construction in some sense, but the usefulness of this is that sometimes, I'm going to give an example towards the end, but sometimes there are computations that are difficult to perform in the 1 plus 1D side directly. But once you map this problem to a 2 plus 1D side, it might happen that you are able to perform this computation using techniques in TPFT. Basically, the upside is that the 2 plus 1D TPFTs are studied so much that a lot of techniques there. So you can do some computations when you map the problem to this.
They're not supposed to be the same things. The two sides of the.
So if you do a dimensional reduction here, then you push. So in the literature, this is sometimes this whole setup is sometimes known as symmetry topological field theory. And for some other people, this is known as topological holography. But it's not really usual holography in any sense. This is just user mnemonic. Really different from ordinary holography. But sociologically, like similar to usual holography, what people have been interested in recent years is to sort of fill out, say, the holographic dictionary. You start from observers in 1 plus 1D site, and you want to understand how that observer is represented in this 2 plus 1D picture and vice versa. Let me give an example. So the canonical example of this is to consider say a local operator here. So this was explained in a paper by Sahan in the ODS a few years ago, and collaborators. If you have a local operator in this site, let's say we have a G symmetry and local operator is charged under this G symmetry. And on the 2+1 this site, since we are gauging the G symmetry, this charged operator must be attached to a Wilson line. There will be a Wilson line for the G gauge field stretched in the bulk of this theory. This Wilson line ends on this side, or tilde is basically the same as the Wilson line can terminate on the dirichlet boundary. There is a more general picture for more general symmetries. And what I want to do is to sort of add a new entry to this holographic dictionary. Now I want to start from 1+1 this theory defined on a manifold with a boundary with some chosen conformal boundary condition. And I want to understand what's the corresponding picture in the 2+1 this side. Yeah, since I want to discuss some applications at the end, I'm going to be very schematic here. I'm going to just tell you everything at the level pictures. Let's say we start from 1+1 this theory Q. This is CFT. You pick some conformal boundary condition B. And the theory has some global symmetry described by a fusion category of topological line operators. And this boundary condition belongs to some modular category M. And this is our proposal. On the 2+1 this side, so inside the bulk TQFT is still the tri-zero TQFT based on this fusion category C. And here, again, you have Q tilde boundary condition. And here, you again have a dirichlet boundary condition. But there, you need to specify what's happening on the top of this picture.
Sorry, maybe one question. If we consider this case and then, but in 2D case, we have a spontaneous interbreaking of the group G. What would happen in the higher units?
Sorry, in this side?
Yes, yes,
It was spontaneously broken G symmetry.
yes.
So if you have a finite group symmetry G and if you have a spontaneously broken finite group G symmetry, then that results in a multiple vacua from consolidation sectors. But yeah, actually I didn't specify all the assumptions, but I assume my CFT has a unique ground state, meaning that G cannot be split. So okay, so to describe the proposal, I need to tell you some facts without justification. This is a fact of light that the topological boundary conditions of this tri-zero objective these are in one-to-one correspondence with the modular categories and on its the fusion category X. Just roughly speaking, for people who know what these are, so the tri-zero you can define it using the state sum construction, and then when you have a boundary, to each like tetrahedron, you can assign a weight that's defined by the boundary situation for the modular. That's roughly how it's defined, but it's not really too important. But this is the known fact. The proposal is that on this side of the TPFT, we have another topological boundary condition. It's precisely labeled by this modular category M, which on the 1+1 this side, it was the multiplied of this conformal boundary condition. Now here we have an interface between Yichul and this modular category boundary condition M. This is a topological interface, so you know that's beyond the line. This side we have an interface between M and Q tilde. So I call B tilde. The claim is that if you start from this picture and imaginary reduce, then you will be able to go back to the 1+1D picture. Just to move on, so if you start from a boundary changing local operator in the 1+1D side from a B1 boundary to B2 boundary conditions, and we propose that in the 2+1D picture, this boundary changing local operator becomes this extended configuration. So this alpha becomes a topological interface in two topological boundary conditions, M1 and M2 for this TKP. So M1 and M2 in this side was multiplied of boundary conditions for these two boundaries. M1 and M2 doesn't have to be the same necessarily. Okay, so going back to the question of this boundary to algebra that we had defined on the 1+1 this side. Now the claim is that irreducible representations, and so I will explain. Irreducible representations of this boundary to algebra are in one-to-one correspondence with these topological interfaces. Are in this TKP picture. So let me just mention that for us this is just sort of conjecture if you wish. But for special case where M1 and M2 are the same modular categories, and when you translate all the pictures into a mathematically rigorous statement, this is a mathematical proof in that special case. And then there are several papers, but let me just get some. Yeah, I'm almost running out of time, but I want to discuss some applications. Can I take maybe 5 minutes? Okay, so. Okay, so. To discuss some application, the study of entanglement entropies. Okay, so the setup is that we have the 1+1D theory defined on an infinite line. I'm going to take the finite interval in my sub-region. There's a length L, and then outside the interval will stay complete. And there is a well-known relation which was observed by many people. We first write down names. There is a general relation. There is a following dictionary which seems to be quite general, which is that when you take the reduced dense matrix for the ground state on this side, say row A, to define the entanglement Hamiltonian to be as usual. In general, it so happens that this entanglement Hamiltonian is essentially the same as the Hamiltonian. Let's say this theory, it could be a continuum theory or a lattice theory, but let's say if there's a lattice theory, this was at the critical point. And what you find is that this entanglement Hamiltonian generally agrees with the BCFT Hamiltonian with some chosen conformal boundary conditions. This was numerically checked in many examples, first by this author. There is a really nice purely CFT understanding of this relation, which is very explicit. I wanted to explain it, but because of time limit, I'm gonna skip this. But there is this general relation, and also look at the entire entanglement spectrum that coincides with the BCFT spectrum. So the spectrum of boundary changing local operators. So they wonder which boundary conditions that's determined by your UV choice. For instance, if you start from a critical equanimizing model, and there is a tensor product Hilbert space in the UV, and you have a clear decomposition of a Hilbert space. In the case, if you tune the system to the critical point, and consider the entanglement Hamiltonian for a single interval, then it flows the boundary BCFT Hamiltonianizing CFT with the G2 symmetric boundary conditions. But there are many examples.
Yeah, I would expect you could put any boundary condition and then when you take the limit, the dependence should go away.
Yeah, so yeah.
Is that what happens? Or?
Well, which limit?
You cut out a little circle and you're putting a boundary, right?
Yes.
Then so that you can put many different boundary conditions. But then you're supposed to take the limit when those boundaries become very small.
Oh yeah, so
I would expect that the universal part of this.
oh yeah, so the universal part. So let me just say this. So so there is this choice of boundary condition, but the universal part doesn't depend on these details. If you compute the entanglement entropy, and the leading universal piece doesn't depend on these choices. There are subleading terms. Let's say on this side, the entanglement Hamiltonian was mapped to BCFT Hamiltonian in this Hilbert space. And there is a subleading constant piece determined by the G function of these boundaries. And the further subleading terms are determined by the entire entanglement spectrum.
I would mainly think that for the purposes of entanglement entropy, we should throw away these G1s and G2s as UV details.
Yeah, but there could be one perspective. So we are thinking about this for quite a while, but yeah, these are, we could regard this as UV details, but these are details that you can also match in the IR. From UV to IR, so let's say you start from the Ising chain, spin chain, the UV, and really numerically compute this entanglement spectrum. And after some taking care of finite scaling problems, you can actually see the numerically that this entanglement spectrum precisely agrees with the IR BCFT spectrum. So it's something we can match. And yeah, one can also do that analytically for the case of Ising model. And there are many other examples, spin and Heisenberg chain.
Is it with the assumption of some symmetry that these details matter, or even without any symmetry?
So far, it's without any sign.
Yeah, I would expect that if the entanglement spectrum depends on such details, it's not really universal thing.
Yeah, so yeah, I think that's a one valid perspective, but we can also decide to keep this. So the title of this paper, for instance, is a physics at the entangling surface. Tells us something about the entangling surface. So maybe this is not the probably not the most interesting aspect of entanglement entropy, but some final detail that one can try to compute. Okay, so yeah, sorry for going over time, but the point is that on this side of the story, we know that this spectrum organizes into the irreducible representations of the this boundary tube algebra. This means that we can block diagonalize the entanglement, the reduced dense matrix. So its block is the irreducible representation of this. So if you take each block, each of them are not dense matrices because their trace is not normalized. We're going to define this new object where I just normalize the trace to be 1. In the literature, one can compute the von Neumann entropy for each of these blocks. And in the literature, these are called symmetry-resolved entanglement entropies. This is defined by minus trace rule of this guy. There are various motivations to study such objects, but let me just briefly mention that they are studied both theoretically and experimentally. But the thing is that one can explicitly compute that quantity using this PQFT picture. It's gone now. But let me just tell you the answer and try to wrap it up. So you can compute this quantity using PQFT techniques. And then the leading behavior is the same as before. So the leading logarithmic behavior doesn't change. Then the boundary G functions also doesn't change. They don't change. And at the same order as the G functions, there is a additional data, additional bits. There are press comes in powers of double epsilon. Let me just explain briefly what these numbers mean. Sorry, so the is there are some real numbers are called quantum dimensions. So in the PQFT picture, this alpha is a topological interface between M1 and M2 boundaries. BB1, BB2, there are also some topological interfaces. And quantum dimension of a topological interface is defined by the expectation value of a closed loop. Something we can compute in principle. I know in many examples. This and also this number. This is an integer. This is the dimension of the TQFT Hilbert space. On a disk, where you divide the boundary of the disk into 3 dimensions. here we have M1 boundary, here we have M2 boundary, here we have the Yichul boundary, and each of these boundaries are divided by these topological interfaces. The details are not been planned, but I just wanted to tell you how these are defined. And I'm gonna, I really try to wrap it up, but just to give you more intuition, let me make a few remarks about this formula and then finish. Some comments. Okay, so to restrict to ordinary finite group symmetry, we use G-symmetric boundary conditions. Then this addition or contribution reduces to following expression. In this case, alpha is just labeled by the ordinary group representations, and d alpha just corresponds to the dimension of the representation. And this result was previously obtained by many authors. So if it's an ordinary symmetry, you can derive this result without relying on the techniques. This paper computed this quantity using some algebraic field theory approach. And there was another more recent paper by Suzuki, Channel, and Wolfrey. And they use the same BCFT approach. So in this special case, our formula reduces to this known result.
We subtract the standard entanglement and to be a single lattice when you contribution. Sorry, the logic. The logic is that we subtract standard entanglement and to become the symmetry-resolved one single lattice when you
Maybe you should finish.
Oh, yeah, sorry, yes. Okay, so that was comment number one, and comment number two is that if you focus on now take the general fusion category and consider the case where B1 and B2, the two boundaries are the same, and then they form a one-dimensional red. A special case, so this is like a symmetric boundary condition. The literature is sometimes the strongly symmetric boundary condition. Let me not explain what that means. It's just a singular one-dimensional ring red. In this case, this formula reduces to this additional contribution reduces to this. The denominator is defined by some of our scalars of the topological lines of their common dimensions. One remark is that if you take this case, then every representation alpha of the boundary to algebra is included in the entanglement spectrum. So this satisfies some kinds of completeness hypothesis. And then each representation, if you complete the symmetry-resolved entanglement entropy, then this is what you get. Now you can take the special case where the alpha is the trivial representation, so the invariant states. And this becomes, in this case, this column dimension is just one. And you get this quantity. And then for whatever it's worth, this is the same quantity. So for topological entanglement entropy for this bulk 2 plus 100 TFT, that was defined by 5 and Preskill. And also independently by Lobin. So we do not know if this is just a coincidence or there is a deep reason or not, but we can say that somehow the 1 plus 1D symmetry resolved entanglement entropy was about 2 plus 1D topological entanglement entropy. If you wish, this is like a part of the this holographic dictionary for this topological holography. So let me stop here, and I'm so sorry for going over time, and thank you for your attention.
So these first terms are known to be monotonic under RG flows. Is anything known about the?
That's a great question, but yeah, not that I know. Yeah.
The boundary condition that participate in a specific representation all have the same G.
Oh, yeah, that's no, generally no, but yeah, generally no, yeah.
How can you write it? Which G is it?
Oh, so here I fixed
The ratio,
P1 and P2.
the ratio is related.
Yeah, so I don't know if this was the original question, but this you can also show that these column dimensions are yeah, so the ratio between the G function and the this column dimension. This is the same for all the boundary condition, the same number. But yeah, each of these can be different. For instance, if you start from a boundary B with some G function G, and you connect the topological line here, and define a new boundary. And the G function for this new boundary is equal to the column dimension of this topological line times the original function. And, yeah, and there is a relation, but in general they are different.
So the right hand side depends just on alpha and not on the original boundary condition. That's my question.
Yeah, so the right hand side depends on the choice of boundary conditions, and also the choice of the representation. Yes. That's right.
The other question? If not, let's thanks each other.